All right, folks, here we go. Welcome back. Good to see you, hopefully, well, virtually at least. Um, Hoping that you're coming back with ready to see some kind of interesting stuff that we got for you. Today's notes are going to be about basically magnetism, what we call B fields, and Earth's magnetic field. All right. I got mapping with me on Tuesday, and we'll do some big mapping with me on Thursday. I'll show you a simple mode next Tuesday. All right. On Friday, you've got open note quiz. We'll talk more about that as we get there. Looking at next Thursday is probably the test day for us. Okay. You can find online on Schoology the non-video portion of this. If you want to look at that instead of hearing my voice and whatnot. So this one will be challenging. As most of you know, I like to walk and stand and move and do stuff like that. Sitting here is going to be definitely really a challenge for all of that stuff. Okay, so but we'll persevere. We'll get through it. If you have questions about anything with this, we got office hours Thursday morning and Thursday after school. Feel free to email me any questions that you have or anything like that. All right, let's start it up. So magnetism and magnets. All right. First one you want to write down. All magnets are a result of a moving electric charge. Now, when we look at this concept, we'll explain this more in depth as we go throughout the chapter, but this becomes a big one for us, just because that movement becomes actually very, very crucial for us to create this concept of magnetism. Okay. So if they all must, like I said, we'll get into more details with this. So if they're all going to be moving, I'll show you exactly what we mean later on with this thing. Okay. So all magnets have two poles, north and south. I don't think that's anything that you're not aware of. I know that we're used to looking at like a kitchen magnet. We don't necessarily see two poles with that. But the thing to be aware of with a kitchen magnet is you only really have one pole exposed. The other end is usually, glued or has some sort of adhesive to whatever thing you're keeping or showing off in front of you. Okay. But if you think back to middle school, all of those magnets had two poles. They had a north pole and a south pole. Now, some can get flipped or some can get reversed, but for the most part, you're going to see they're going to have two poles. All right. Like poles repel, opposites attract, very similar to what we talked about when we talked about charge about a month ago. All right. Where we said, hey, positives repel, negatives repel, positive, negative attract. Here we go. North and north repel, south and south repel, and then north and south are going to attract each other. Pretty straightforward stuff. All right. Magnetic field lines are drawn from north to south. Now, make sure you note this real well. All right. Because this one is different. When we have field lines here, we're going to draw a bunch of different field lines for you. They do start at the north end and they do travel to that south side of it. All right. So just be aware of that. That's a big one, that we draw our arrowheads properly and really show this off correctly. Okay. And a magnetic field line is symbolized by B. I know it's weird. I tried to do some research on it, and there were a lot of discussions on, kind of some thoughts on who came up with this model or came up with why it was B field, but nobody really had a definitive say on it. They didn't want to use M because they they didn't want to confuse people with mass and stuff like that. So they use B fields. Less than ideal. Sorry about that, but that's kind of the way that they work it. Okay. All right. So drawing magnetic field lines for us now. Like we said, magnetic field lines are drawn from the north magnetic pole, and then they end at that south magnetic pole. This becomes a really, really big deal for us just because we need to be able to be consistent with this. All right. So when we see something like a bar magnet, what we're going to see here is that all of those field lines start from that north, and then they all start to kind of curve or bend towards the south end of that magnet. Now, something else to be aware of here is if you're looking at the south end of this magnet, is that we see what appear to be randomly drawn in lines. Those lines are coming from somewhere. Now, whether or not they're coming from this individual magnet or coming from a different magnet entirely, that's something that we can't determine at this point in time. But likely, if you're looking at the angled ones coming in, those are probably coming from that north the north end of that magnet. The one that's coming directly in, that may come from the north end of the magnet. It may also come from a nearby magnet if that's something that is an option for it. Okay, so don't get too tripped out about that. Okay, so when we talked about electric fields, hopefully you remember what they look like. Okay? Electric fields. Remember when we put two parallel plates oppositely charged, that charge wants to move from the positive to the negative. Or that's the direction that it's going to go, especially if we put that test charge or that charge in there. What we see is that that positive charge there really wants to get away from the positive because it's not comfortable there. It's not where it wants to be. It wants to be next to that negative because, again, opposites attract and likes repel. All right. So when we see B fields are just going to show us the direction of the compass needle. All right. What that means is that we're going to see how these magnetic fields actually are going to track in real time tomorrow and also later on in the week. But really what we see is that that little compass needle there is going to point in the direction of that B field line for us. It becomes really, really nice because it becomes, something that we can move, something that we can adjust, something that we can take and put in a different direction, and it will still show that. If you're really bored today and you want to look up your compass app on your phone, eventually you're going to have to figure out where north, south, east, and west are in your room, in your office, wherever you're watching this video. So get it out and see. And just kind of walk around and see how that compass needle is going to change. Now that's going to be a little different because that's working with the Earth's magnetic field, which we'll talk about in a second. But the really interesting piece is that the compass needle is just a small magnet that's free to get pushed around by a larger magnet. Now, granted, the one on your phone is not necessarily a small magnet. Okay, that has some different aspects to it than what we're looking at here with this little spot magnet or this little spot compass. Okay, all right. They are not the same. Sorry, but for the most part, they still are going to represent the same thing for us. All right. So again, that compass looks like a test charge or a point charge, like we show at the left of this one. Okay. So just an example of using some iron filings. Nice little middle school trick for us. What we do is we put on a magnet, put a transparency on there on like an overhead display, and show a compass, and the iron filings will orientate themselves towards the magnetic field and really show what that magnetic field looks like. All right, kind of a neat little thing. All right, again, you can see that compass needle, how it's starting to move and how it's starting to track, and how it's starting to change its angle and its direction based on where that north end, where that south end of the magnet is. Okay, all right. Earth now. Earth is a gigantic magnet, and it's got some interesting quirks to it that I think you'll find it very fun. Okay, Earth's magnetic field. All right. So if we took a compass and put it out somewhere out in space, we would see something that looks similar to that. Okay. Now, when we see this, what we're going to do is this becomes something that is maybe a little different for us, just because we haven't done a lot of compass work in our lives. Maybe in Boy Scouts or Girl Scouts you might have, but likely most of us have not used compasses before. Now, granted, there are going to be some small subtleties, like the Iron Range in northern Minnesota is going to add to some of that kind of dilemma where we'll see that compass not be real consistent there. But for the most part, as long as there's not a ton of magnetic rock around us, this compass will point tried and true. Okay. So what we see is if we talk about this compass, so since a compass is just a small magnet, it really does set up for something that's going to be a little different than what we've ever seen before. All right. So remember now, when we talk about the rules of a compass, the north end of a compass will be attracted, or will be attracted to the south end of a magnet. The north end will be repelled by the north end. So if you look at the little compass on here, what you're seeing is the red part of that compass. That's the north end. Okay. So since opposites attract and likes repel, which end of the compass needle points north? Yeah, it should be the north end, right? And again, that's pointing towards, that's going to give us that north direction that we have. But that means something's different. Because if you look at this model of the Earth right here, it means that that compass is pointing north. but it's pointing towards our North Pole, which can't happen. The reason it can't happen is because that compass needle is a small magnet. Because it's a small magnet, north cannot point to north. That's not how this works. They're repelled. So, or Earth's North Pole is actually magnetic south. Now, I'm going to let a moment for that to sit in, because the first time I saw that a couple of years ago, that totally blew my mind. Like, holy cow, seriously? Like, I've been taught wrong the entire time, my whole life? And no, not really. It just happens to be that for us, when we set up the direction of that compass, that north was north and south was south, kind of like when Ben Franklin talked about, the direction of charge. And he said positive charge went one way. So what ends up happening is that we see the north geographic pole is actually the south magnetic pole. And the south geographic pole is actually the north magnetic pole. So make sure you got an understanding of that. Make sure you get that written somewhere, because that does become a really, really popular question for us as teachers that we like to ask. And it is different. I'm going to say that as best I can, just because it's something that we're not used to seeing. Is that the north part of a compass points north, but it points to the south magnetic pole. Okay. All right. So again, big game changer for us. All right. So Earth's magnetic field does provide some nice things for us. It does allow us to be protected from the sun. And the way that it allows us to be protected from the sun is by that solar wind. That solar wind is all just the radiation from the sun. And the Earth's magnetic fields do allow us to kind of have a nice resistance to that. All right. Now you will notice that some of that on the north and south pole, geographic north and geographic south pole, some of that radiation does sneak in. Okay, just because there is that spot where now it's trying to push straight up and straight down, and it just doesn't have that buffer, so to speak. And this will flex and move. It's not a rigid force or anything like that. All right. So what we see is that this is what we're protecting against: is a solar flare or a solar event, where all of a sudden now we see that sun release some of that energy from us. Okay. And it produces northern lights and aurora borealis, and also southern lights too. And this is at the poles, typically where you saw that kind of little bit of electromagnetic radiation coming in. All right. There are some absolutely fabulous videos on this. If you get a chance, check them out. Especially from the International Space Station, there are some really, really weird looking videos there. Okay. If you get some time, check those things out. All right. Again, something that we probably know. We have a solid inner core and a liquid outer core. All right. What we start to see is that the movement of these two causes our magnetic field. Okay. Something to be aware of. This is something that kind of struck me as weird. The location of our south magnetic pole has been moving, and it's going to continue to move. They're saying that it's moving faster than it has in the past, and usually about every 5 or 10 years, they will start to measure where it is. But because of its quickness and its movement right now, they've actually had to start to measure a little bit more often, so to speak. And they're saying that it's fast tracking from Canada all the way out to Siberia. So what that means, let me show you. All right. So Earth's magnetic field's reversals. Okay. So when we look at this, what we're going to see is that it is unpredictable. All right. It averages about 300,000 years. Our most recent reversal was 780,000 years ago. So again, we're due for one of these. Now, is there a time frame where this has happened at this point in time? I didn't do that research. I'm sorry. But again, when we see this, reversals take between 1,000 and 10,000 years. What that means is that our poles are going to flip. All right. Again, because Earth has inner and outer cores, the liquid outer core is why we have a magnetic field. Again, we see that movement of charges. We see the movement of those charged particles, and what they do is they create that charge for us. All right. As we see it, we get these little eddies, these little currents in there that are all of a sudden going to cause us to have that magnetic field happen. This is a model that a gentleman created out of the eastern side of the United States using basically liquid sodium and then spinning it at a very, very high rate of speed. All right. It shows what a stable B field will start to look like. All right. So as you see this, you can see where the magnetic fields are. Now, the interesting thing about this is that as we say, here's our stable one, here's what it looks like in 500 years during the middle of that reversal. Okay? This is what it looks like darn near in the middle of it. Okay? This is what it looks like 500 years, and that's the stable B field again. Now, this freaks people out because they're wondering, well, what does that mean for us? Are we going to lose our magnetic field? Are we going to have higher incidences of, skin cancer and stuff like that? Possibly. But the thing is that there's still a magnetic field around us. Now, it may mess up some of our electronic stuff, and it may mess up some satellites and stuff like that. But the thing is that it's not something that we have to be super, super worried about in our current state of life. Okay. So it's just saying that at some point in time, maybe when your kids or your kids' kids or your kids' kids' kids or whoever is there, you'll see that they may have to go through this and may have to start the experience with it. But it's not something that we're going to worry about. Okay. Here's your Geodynamo experiment. Again, something kind of interesting to look at and see if you have time and want to. Like I said, huge spinning sphere of sulfur or of sodium. Pretty scary stuff in actuality. Okay, so because magnets don't have a positive and negative, they instead are going to have kind of this north and south pole. So for us, when we see north and south poles, what we're going to see is that a magnet can't really be separated. If you go ahead and you snap a magnet in half, what will take place is that magnet is not going to just stay in half, meaning you're just not going to get a north magnet, south magnet. What you'll actually end up seeing is you'll get two smaller magnets with a north and south magnetic pole, which is kind of crazy, right? So that's how we're able to kind of fix magnets, so to speak, or do that. All right, well, that's pretty much it for the day, folks. I think you've heard me talk enough for the first time out here, all right? So hop up onto Schoology at some point in time. What you're going to find is that there's homework up there for you. All right, it's predicting magnetic fields. It's a combination of book work and some non-book work questions. This one will be due by 5 p.m. today. It'll go in as a homework score, but also when you complete it, it will count as your attendance for the day. All right. If you get this done after 5 p.m., you're still going to be. I'll still try to fix it, but likely it'll be marked absent. All right. And this is typically how we're going to do stuff. Is we're going to see that you've got a lab right up to do, or you've got some homework, or you got some little stuff that you have to do just for me by 5 p.m. on a given day. That'll give you time throughout the course of the day if you have other stuff that's more pertinent, whether that's work, whether that's helping out your family or stuff like that. Just make sure you get it done by 5 p.m. so that I can get you marked as being here or not. Okay. And if you are bored later today, check out those videos on the Northern Lights. They are pretty interesting, actually. And I think they will be worth your time. They are pretty calming and sometimes they'll even play a little music with that. It's pretty relaxing, kind of interesting stuff. And then if you want to, read about the magnetic field movement and everything along those lines too. Okay. Otherwise, folks, hope you have a great day.